Okay, so this one is using graphs to solve equations and inequations. So we just learned how some methods on how to solve inequations, but this is using a graph as well to help us do it. So straight into the examples, it says number 1, to graph y equals 4 minus x squared and y equals 1 over x on the same set of axes. Hopefully you've remembered all your graphs from your year 11 work. That first one is a parabola, concave down, correct. If I factorize it, it would be 2 minus x, 2 plus x, and that means that I could read off my zeros. So there would be an intercept at positive 2 and another one at negative 2. What is the y-intercept? You should be able to read that straight off the equation. 4, correct. So 1, 2, 3, 4. Okay, and there is my parabola nice and quickly. Okay, this second one is a hyperbola. That's actually the most basic hyperbola that we can get. We haven't moved it sideways, up or down, anything. So the asymptotes that we would have are on the axes. So the horizontal asymptote would be at y equals 0. And the vertical asymptote would be at x equals 0. And other than that, we would have to sub in a couple of points to just get some steepness from there. 1 is always the obvious choice, subbing in x is equal to 1. If you sub x is equal to 1 into the y equals 1 over x, it would be 1 over 1, which is going to be 1. Okay, so I have a point here, 1, 1, for my hyperbola. Knowing that it is a hyperbola, that's enough. I've shown a point there. I can just draw the rest of it in, going through that point like that. If I want one on the other side of my vertical asymptote, I'd sub in negative 1. So 1 over negative 1 is going to be negative 1, so that's down here. And I would have a, whoops, that was a bit wobbly, let's start again. A matching curve down there in the third quadrant. Okay, that's it, we've graphed them. Part B says, use your equation from part A to investigate when 4 minus x squared equals 1 over x. They are the two equations, the two graphs that we've drawn. This is my parabola, 4 minus x squared, and this is my hyperbola, and it has given me an equation where those things are equal. If I'm saying they have to be equal, that's going to be where those two graphs intersect, correct? Yes? Okay. So how many solutions or how many points do those two graphs intersect? 3. Correct. So there is 3 solutions. Okay, how many solutions does it have? It has 3. And it says approximately, what are they? Now it says approximately because they are not nice whole values, and our graph has not been drawn to a beautiful accurate scale. It's been in a kind of a little bit approximate. So just approximately, where are those solutions? So the first one, I'm going to start, x is approximately equal to, so either the wavy lines or equal sign with the dots on either side is also approximately equal to. So the green intercept there was at minus 2. You see this one here is what I'm talking about here. So this here is at minus 2, and they're intersecting just slightly to the left of that. So negative 2.1 or 2.2 approximately. What do you think? So I'm going to say 2.1. Negative 2.1 approximately for that first one. Okay. Okay. Next one, we've got an intercept here, which is just slightly to the right of my vertical asymptote. What approximately do you think that would be equal to for an x value? 0.1 or 0.2, somewhere in there. I'm going to go 0.1 because that's what Max said. Okay? Yeah. As long as it is reasonable and in the right area, I'm not going to be nitpicky of your, I mean, you wouldn't say 0.9 so that's way too far, but 0.1, 2, or maybe even 3, I'd let you get away with that, okay? All right, and There's one more here, which is just slightly under the 2. What do you want to say for that? 1.9, okay. Approximately. Okay, so if you had to try and solve that equation to find out what x was equal to, they're approximately what we have found based on our graph. Okay, they might be a decimal point out here or there, but they're close. All right, let's go on to the next question. Question 2. Graph y equals, gentlemen, graph y equals the absolute value of 2x minus 5. Remember how to graph an absolute value graph? Yes, maybe. Okay, well, let's start. I wasn't talking, Rowan was nodding at me. Don't worry. Okay, let's start by finding the intercepts. So let's find when x equals 0. If I put x equals 0 into that equation, I would get y equals 2 times 0 minus 5 in the absolute values. 2 times 0 is nothing, minus 5 is minus 5, but the absolute value of minus 5 is positive 5. So there's my y-intercept. Let's also find out what happens when y is equal to 0. Now, if y is equal to 0, I have the absolute value of 2x minus 5. Now that's the nicest absolute value thing to solve when it's equal to 0, because you can't have a plus or minus 0. You can basically just get rid of the absolute values and it would be 2x minus 5 equals 0. Because when we were doing it before, it would be 2x minus 5 equals a plus 0 and 2x minus 5 equals a negative 0, but there's not really any difference between, yes.
And you get rid of the absolute.
Yeah.
No, how?
That's what I'm just trying to say, because normally we would say 2x minus 5 is equal to a negative 0, but we'd have one a positive version, one a negative version, but because there's no such thing really as plus or minus 0, it's just 0, we can just do it for 1. Okay? All right, solving that, we'll get 2x equals 5, and dividing by 2, we get 5 over 2, or 2.5. Now that x-intercept there is even more important, more special than just an intercept, because that is actually where the point is going to be of the absolute value graph. Because to find a point of an absolute value equation, it is whatever makes the inside of that absolute value 0. Okay, and I've just done that by making y equal to 0 in there. Okay, so to draw it, we have this is going to be used for the rest of this page, so make this a reasonable graph here. So I have a y-intercept at 5. I'm going to put that there. And I have an x-intercept at 2.5. There and there. So we can connect that up. Can even use a ruler, look at that. Because we know this is going to have beautiful straight sides down there. And as we talked about, that 2.5 is the point of the absolute values. So if I were to double the 2.5 and come out to 5, then that would come up to a height of 5 up here to make that symmetrical. You can double check that by subbing 5 into your absolute values if you're worried. Okay, so if you sub 5 in, you go 2 times 5 is 10, minus 5 is 5. Okay, so 5, 5 is another point on that graph. Okay, so there is my graph of y equals absolute value of 2x minus 5. Part B says, write down the equation of the right-hand branch. Okay, because the absolute value, when we find the point, we have the right-hand branch is this side, and this is the left-hand branch, okay? This one over here, this is what the graph of y equals just 2x minus 5 would be equal to. Okay, if I just got rid of the absolute values, this right-hand branch would just be the 2x minus 5. All the absolute values have done is once my graph came down here, instead of going down to the negative values, the absolute value, well, as soon as I go negative, I want to reflect that back up into the positive. Okay, so the right-hand branch would have the equation y equals the 2x minus 5, the function that is inside that absolute value. The left-hand branch is the negative version of that absolute value, which means we want negative outside of the 2x minus 5, which would become minus 2x plus 5. And hopefully that also makes sense because, yes, it does have a y-intercept of 5. Okay, so, yeah, y-intercept of 5. And the gradient is in the same steepness but opposite direction, so minus 2. Yeah? Okay, part C. On the same graph, draw the graph of y is equal to x plus 2. That's a straight line that has a y-intercept of 2, which I'm going to put there. And it has a gradient of 1. So we could just rise 1, run 1, or can't really do that with my graph that's on here. What if I just subbed in 5? Because I've got that point over there. 5 plus 2 would be 7. So 5 plus 2, that's going to be over here. I need a 7 up there. Okay, so that's going to go like that. So I've just subbed in another point. Now, I'm going to have to make that other one steeper, and you'll see why in a minute. I'm going to have to make these intersect. Oh, okay, they're just going to intersect there, barely. Okay, all right, so, hence, find the points, this is for D, hence find the points P and Q, the points of intersection. So I'm going to make P this point over here, and Q this point over here, and I want to find their coordinates. So let's start with P. P is the intersection of the x plus 2 graph with the positive branch of my absolute value, which is the 2x minus 5. Okay, now because they were both y equals, I'm going to say x plus 2 is going to be equal to the 2x minus 5. Yeah, is that okay? Solve that for x, so let's subtract the x across to the right hand side, so that would become a 1x over here, and then add the 5 back the other way would make 7, or let's switch sides, x equals 7. Okay, if I found that x is equal to 7, P is a point, not just an x value, I need to find the y value. Sub it back into one of your original equations. So this is going to be the easiest one here, y is equal to x plus 2. So if x equals 7, 7 plus 2 is 9. So my point P is going to have the value 7, 9. And looking back at my graph, seems pretty reasonable that that point there would be at 7, 9. Let's find the other one. Again, it is the intersection of the x plus 2 line with the absolute value graph, but which branch is it intersecting now? The one on the left-hand side, which is the one that has this equation. Okay, so that's going to be equal to the minus 2x plus 5. Okay, now, because we have a minus 2x there, let's move that across and make a positive 3x. Subtract the 2 back to the other side, so that equals 3. Divide by 3, and I get x is equal to 1. Sub that into the highlighted yellow equation. 1 plus 2 makes 3. So the coordinates of Q is going to be 1, 3. And again, looking back here, that looks pretty reasonable. Q looks like it could be 1, 3. Okay? All right. E and F are both believe it or not, reading things off of that graph that we've drawn. If it says to solve the absolute value of 2x minus 5 is equal to x plus 2, remember the absolute value graph and my straight line. If I want them to be equal, I'm just trying to find the x values of where they intersect. I just found that in part D. The solutions were x is equal to 1, which was this one here, or x is equal to 7. Okay, so if you're solving those two things, you're just finding where they intersect, the x values for where they intersect. But F now wants it as an inequality. Where is the absolute value graph greater than or equal to the straight line? Let's come back here and look at our graph for a second. Oh, let's just, I'm going to see, you need to see these little bits out here a bit more. Just going to freehand that a bit. Okay, so I want to know where the absolute value graph, which is the red one, is above the yellow line. So that would be from the point of intersection, the red graph is above there. Yeah, and it is above the yellow line here. Okay, so there's two separate solutions. So remember that this, on that first one, that value is a 1, x equals 1. So it would be x is less than or equal to 1 for the first one. Oop. Or the other one, going back, that other value was 7, wasn't it? And it's going to be greater than or equal to 7. Okay?